This is problem number 25 from chapter 6. I've copied the picture right here, but you can see the problem. When the three blocks in this figure are released from rest, they accelerate with a magnitude of 0.5 squared. Block 1 right here has a mass m. Block 2 has a mass 2m. And block 3 has a mass of 2m. What's the coefficient of kinetic friction between block 2 and the table? So we know that there's friction right here. Obviously, there's not friction here because it's not touching the table. And so we have to figure out what's going on. There's a couple different ways to go about doing this problem. The first way that I did it when I hadn't been doing AP Physics for many years is I did this. This is my homework solutions. And you can see right here that I drew my picture. I didn't even do a free body diagram here. I did individual free body diagrams. And you can see right here what I did is I had the normal force, the weight, the friction. We know since we can assume we're accelerating to the right because since block 3 is more massive than block 1, it's intuitive, I hope, that we are going to be moving in that way. So since our movement's in that way, our friction is going back this way. And then, of course, I have the tension. You hopefully realize that the tension from block 2 is the same as this tension right here from block 3. The tension is the same around the whole rope. And so I did different free body diagrams for the y direction of block 2, and then the x direction of block 2. And then I have block 1, and I said the x direction because it looks like it's the up and down. But whenever you're dealing with a rope, you consider the rope to be your whole x direction. And so I have the free body diagram worked out, F equals ma for that. And then again for block 3. And then I substitute a whole bunch of stuff in here because obviously I have the tensions here, which I don't know. Now you can take a look at this and pause the camera and think about how to do it this way, or you can continue watching the video and see a much simpler way to do it when we just completely don't worry about the tensions. So this is having 3 separate free body diagrams and solving, and it works, and we get an answer. But now let me show you a different way. So our different way, I'm still gonna essentially draw a free body diagram, but to save time, I'm just going to do it right on top of my picture here. So we have 2 mg as our weight here, mg as our weight there, 2 mg as our weight there. We have tension here, but this tension is the same thing as that tension. And this tension is the same thing as that tension. I'll call these ones tension 1 and these ones tension 2. So that it's clear to you that this tension is not necessarily the same as that tension, but what the tensions actually are, we don't care about. We also have more forces. So I have force normal right there. And as we already discussed, I have the frictional force right here. So if you have no idea where to start, a good idea is to start with drawing all of our forces here. So done. Now, again, like I mentioned before, if we are dealing with a rope, and especially if we have frictionless or massless pulleys, which, do they even mention that? No, they sure don't. But right now in this chapter, we have not dealt with any pulleys that have mass. So you can assume they're massless pulleys, which means you can assume that this tension across this rope is the same. Now, if we're doing that, like I said, this whole thing is our x-axis. And so what that means for us right now is that I'm going to do F equals ma for the whole thing. If I consider my whole system in my F equals ma, so sum of the forces equals mass times acceleration. And again, this is like my x direction because my x direction curves the rope. But if I consider the whole system, then that makes my tensions internal forces, which means I do not need to include them because essentially if this is my positive direction, this would be positive T2, that would be negative T2, and T2 minus T2 would be 0. So we don't even need to put that because it's not going to equate to anything. So anyway, here we go. Let's think about all of our forces in the rope direction. So I have 2 mg, specifically from this one right here. Then I'll travel, don't worry about my T2, T2. And I'm like, oh, look, I have Fk. And that's going in the opposite direction. So that would be minus Fk. I don't worry about my T1 because I would have minus T1 and then plus T1. So again, those would cancel out. So I'm not going to include those. But then I have mg. And again, that's going in the opposite direction as what we've chosen to be positive. Here, I'll put a little plus that way to remember. So that's minus mg. So now we have summed our forces. We're going to set that equal to mass times acceleration. Now, of course, when we're doing mass, that would be the mass of everything in your system. So 2m plus 2m plus m, we have 5m. And our acceleration, we already know it, it's 0.5, but I'll just put a for now and we'll plug in stuff later. Okay, so now we need to figure out something about our friction because we want to know something about the coefficient of kinetic friction. So you have to break this down a little bit. And in order to do that, I'm going to do the sum of the forces in the y direction, specifically for right here. And so I'll choose up to be positive. So force normal minus 2mg equals mass, which is 2m, times acceleration. But since this is in the y direction we're talking about, our block is not flying off the table. So this is going to be 0, no acceleration. So we know our normal force, specifically for this box, equals 2mg, which is fortunate because we know that friction equals mu k times normal force. And so now that I know my normal force, I can say my friction is mu k times 2mg. So this was kind of like a little side note we did once we realized that we needed to solve for our friction. So awesome, we did that. Now let's go back over here. So I'll have 2mg minus mu k times 2mg minus this mg equals 5ma. So all we need to do is solve for our mu k. So let's do it. I'm going to move this whole thing over. Well, okay, let me just solve this and then you can verify for yourself that it's legit. So I have mu k equals 2mg minus mg. And you can see that I'm keeping the signs here, but then I switched the sign there. So I'm essentially taking it to that side, but then bringing it back over to this side because it looks better. And then I'll bring my 5ma over here. So minus 5ma, all divided by my 2mg. So again, you can pause really quick and make sure that I'm mathematically correct, but I'm pretty sure I am. So then I noticed that I don't know what m is, but I also don't care because it cancels out. See you later, m's. So now mu k equals 2g minus g minus 5a over 2g. We can simplify that a little bit because obviously 2g minus g equals g. So g minus 5a over 2g. And now I'll just plug stuff in. So 9.8 minus 5 times the acceleration that we're given, 0.5, over 2 times 9.8. And if we work this out, we find out that our mu k equals 0.372. And you remember that coefficient of frictions have no units, so of course we don't have them, but we're done. And this was a much simpler, cleaner way than that ugly, convoluted way that I showed you before. Now, if you really like dealing with internal forces and substituting all sorts of stuff in, then go for it, have fun. But I highly suggest that if you see a system like this where they don't ask you about the tensions, just take your whole system all together, like we did, and solve. Especially if you already know your acceleration, that's going to be a much easier way to go about it. Draw a free body diagram, sum your forces, and you're done. Bum, bum, bum.